Okay, all right. So that guy is blaming interactions for having lots of things to be studied in physics. Physics exists because of interactions. Remember, physics is the study of forces and energy, where these quantities are basically results of some sort of interactions among things. In this video, we will continue with the big idea of interactions in collisions. But before we proceed to that, note that the collision is not the only event we have for an interaction to take place. Sometimes there seems to be no momentum in some objects, but eventually these objects get one, like in explosion. And in some cases, we see objects having momentum and then after a while, those momenta are gone, like in crash landings. We are going to speak more about explosion and crash landings next time, alright? For now, we concentrate in collisions. To start with, there are two types of collision as per your syllabus: perfectly elastic or just elastic, and inelastic collisions. In order for us to know what type of collision we have, we need to look at the kinetic energy, alright, the total kinetic energy and the total momentum of objects. In a closed system, kinetic energy may or may not be conserved because kinetic energy can be transformed or be converted to some other energy, and that some other form may also be converted to kinetic energy. However, for momentum in a closed system, we can always say that it is conserved because there is nothing which momentum could be transformed into. Unlike in the case of kinetic energy, there are many other forms of energy. We do not have any other form for momentum. So in these two types of collision, momentum is conserved. We can just take these, alright? If the kinetic energy is also conserved, meaning the combined kinetic energy of objects before collision is equal to the total kinetic energy after, then we say that the collision is perfectly elastic or elastic collision. Otherwise, when part of the total kinetic energy is lost or converted to other forms, meaning the kinetic energy is not conserved, we have inelastic collision. So that's it about the two types of collision. But we are not done yet. Let me organize my screen first. Okay, this one, we make it smaller so we can concentrate on this perfectly elastic collision or the elastic collision, because when it comes to perfectly elastic collision, you need to know some shortcuts how to tell whether it is really perfectly elastic collision or not. And if you would start from the two ideas, conservation of momentum and conservation of kinetic energy, likely you would be spending so much time. So we are going to do it now so that you could have some kind of a shortcut representing the combined conservation ideas for perfectly elastic collisions. Imagine we have a closed system with a red object and a green object, and these two are moving towards each other. Green from the right, like that, and the red is moving from left to the right. They will bump into each other, collision later, alright? The red object has a mass m1 and the green is m2. We also have here initial velocities, u1 for red and u2 for green. After collision, they will have velocities too, v2 for green and v1 for the red object with mass m. We know that the total momentum before collision, which are the momentum of the red plus the green's m2 times u2, this must be equal to the total momentum after collision. So m1 v1 plus m2 v2 here. Alright? If we combine the momenta, initial and the final momenta of one object, same colors here, we will have m1 u1 minus m1 v1. We transpose it from the other side of the equal sign. For the other, we do the same. So we have m2 v2 minus m2 u2. We have a common factor here, so let's do this. Okay? At this side, same thing. And there we go. Now, what I'm thinking, guys, actually is to find the ratio between two masses m1 and m2. And it's gonna be easy now, you see? We can just do the ratio here. And this m1 over m2 should be equal to this. Alright? Now we have this. Let's separate this and put here. Okay? And just erase the other stuff on our screen. Anyway, all those are already represented by this equation, the ratio, from the conservation of momentum. Now, we see the other one, the kinetic energy. Conserve also when the collision is perfectly elastic, alright? The kinetic energy of m1 is half of this mass times the square of its u1. We are talking about total kinetic energy, so we can add the kinetic energy of m2, which is half of that mass, times square of u2. Same manner, we add the kinetic energies after collision. For mass 1, same formula but using v1, so this. And for the other, 1 half m2 v2 squared, like that. Okay, all these terms have 1 half in it, so we can just erase all those. to make our life simple. And then we combine the colors. I mean, we determine the momenta involving only same object, like the way we did a while ago. And so we should have this, all right? All right? Now, here's what I want. The ratio between masses M1 and M2, and this is it. We do not need this anymore. We already have this, and this is from the conservation of kinetic energy, so we can put it here, okay? I think better to put it here so we can have more space. Okay, that. Let's make it smaller, all right? Okay, here we go. These are both having the ratio, see? Those terms at the right side of the equal signs, they can be equated. Let's copy this, okay? And this one too, all right? These two must be equal. I like to color my screen. In most of my videos, I always been doing this. So I'll color this one, all right? Is it all right? Okay, what I want to do now is to combine expressions involving the same velocities or speeds of the same object. Cross multiplication here, so I can have this. Same with the other. Now, do you remember your maths about the difference of two squares? We have those here. In the numerators here, this and this, difference of two squares, yes? We know that if we have that, we can factor it like this, like a product of sum and difference. And we can easily see that this may be cancelled because anyway, this is equal to 1, alright? This entire expression here is just equal to u1 plus v1. And for the other side of the equal sign, putting the factor of difference of those squares, we have this. This can be erased because equal to 1. Now, what we have here is an equation that only needs information about the velocities before collision and after collision. And we can already tell whether a collision is perfectly elastic or not. Let's erase this for space again, okay? Now, if we are to rearrange these, like bring the initial velocities together and final velocities together, we will have this white equation here. The u1 minus u2 and v2 minus v1 here. If we take the difference between two initial velocities or two final velocities, then what we are going to actually get is the velocity of one object that is being measured with reference to the other. Like what would be the velocity of mass 1 when the observer is mass 2, which is also moving. Okay? The magnitude of that is the same when the velocity of mass 2 is being observed by moving mass 1. Regardless of which is doing the measurement and which velocity is being measured, the magnitude are the same. That is why it is more popular for physics people to use the word relative speed rather than relative velocity in this case. So before collision, this part, we call it relative speed of approach. And after collision, this part here is called relative speed of separation. And if the kinetic energy and momentum are both conserved, meaning the collision is perfectly elastic or elastic collision, then we say that these relative speeds are equal. Alright? Same relative speed of approach and separation. Alright, lastly, we apply this to a question from previous exams. Let us make this smaller so that we can put the question here. Alright? Okay? It doesn't look nice. Better switch places. Alright? Alright, here. We put this there. Okay, that's better. Now, in this question, you are given velocities before collision here and those after collision. And if you may notice, the question did not even mention the masses. Correct? Nothing here. We have here an elastic collision, so we should find the relative speed. Relative speed of approach should be this. UA minus the negative of UB or UA plus UB. This means that if a person is in A and measuring the speed of B, the measurement is the sum of these speeds. For the relative speed of separation, we have VB instead of V2 minus VA, which is the V1 in our equation. These two are equal in elastic collision. So the answer to the question here should be this, option A. Okay guys, that's all for now. See you next time. Bye.